everyone. My name is Hunter Ballard. I'm a senior student studying biology and working under Dr. Anusree Mukherjee in the chemistry department on this research. This is a little bit of information on some photoinduced electron transfer pathways and some transition metal complexes that we are exploring for use on these applications. Just to start with, how many people here have any chemistry knowledge or background? So I know we're done. Okay, great. All right, well, we'll take a bit more of a 30,000-foot view. That way I'm not just making everybody bored the whole time. So essentially, we are looking into alternatives, energy sources as opposed to fossil fuel. Within today's framework, everything is based around fossil fuels. There's a constant search for something that is sustainable and reliable and is clean. You have things like solar energy, you have things like wind energy, you have hydropower dams, but you know the sun's going to go behind the clouds, and rivers can dry up, and winds can die down. So we're looking for something that we can actually use to convert photo light energy into chemical energy, because I mean that's a pretty consistent light force, depending on where you're at. And this gets into the weeds a bit about photocatalytic hydrogen production. That's the actual technical mechanism of it. But what we're focusing on is more of a preliminary study of the first steps. And that preliminary investigation is into these photoinduced electron transfer pathways. Okay, what does that mean? PET, which is what we're going to call the system, essentially is when you have light is going to come in, strike a system, and it's going to excite electrons in that system to jump from one energy state to a higher energy state. It takes energy to make that jump occur, and they stay up there for a period, and as they fall back down, they release energy in the form of light, and they're also susceptible to being captured at that time. That is actually what we call fluorescence. So you've seen sort of fluorescent jackets, things like that. Light hits it, electrons excited. As electrons fall back down, it gives off a photon, gives that shiny fluorescent look. And like I said, as those electrons fall back down, they're susceptible to being captured by things called quenchers, which essentially they take them and they can make a radical formation, which is when you have splitting of electrons. So one electron goes to the quencher, one electron goes to our initial excited fluorophore, also called a photosensitizer. So that's our basic system. We want to excite electrons, and as they fall back down, we want them to be captured. That radical formation is very unstable. Electrons can be transferred. That transfer of electron transfers energy, and downstream of that, we're not exactly sure how to crack this yet, but downstream of that, we can use that to essentially produce or capture energy for other uses. So as I mentioned, this is a preliminary investigation into specific transition metal complexes. The one that we chose to look into the most was cobalt dimethylglyoxime. That's this complex right here. We chose that because we know from the literature that it's supposed to be capable of producing hydrogen photocatalytically. And as I mentioned earlier, the downstream endpoint we want is the production of hydrogen via this incoming light and electron excitation. So the way we chose to study this is essentially we take our photosensitizer, the thing that is excited by light, and we take our quencher, which is this cobalt dimethylglyoxime, and we want to test the effect of it and just verify, yes, in fact, this will quench our photosensitizer. And our photosensitizer in this case is a compound, it's a fluorescent compound called rose bingle. It's a vibrant, beautiful pink solution, or pink dye that is soluble in water. And so the way we tested that, like I said, is we essentially just combined the two in a controlled environment to understand the effect and the relationship of the concentration of our quencher to the concentration of our dye. So this first graph right here, if you can see this green line, I know everybody's need their reading glasses because I got this small poster, but this green line represents when you have our dye, rose bingle, in a solution with none of our quencher. And this y-axis right here represents the amount of intensity, the emission intensity, the amount of fluorescence, how brightly it fluoresces. You know, at the higher the number right here, the more it fluoresces. So no cobalt dimethylglyoxime, And then we slowly start adding equivalents of covalents. And what we see is a pretty obvious relationship between the amount of cobalt dimethylglyoxine and the quenching effect it has. In other words, the more cobalt dimethylglyoxine you have, the less our dye is going to fluoresce. So when we get up here to 10 equivalents, which is just in numbers wise, it's 55 microliters in a total of 2,900 microliters of solution, so a tiny, tiny amount of it. It basically produces all of the fluorescence in our system. Another thing we wanted to control for is, are there other molecules in our solution that could be assisting in this, that could be quenching our dye and producing the same effect? So we control for that by essentially testing with oxygen. And you can see right here, we have our dye with the standardized amount of water and no added water, because oxygen in the water is what can quench it. And then we just start adding more equivalents. So we actually added 20 microliters and 100 microliters of water, because water may not be as potent of a quencher, so you might have to add more of it to see an effect. What we see here is there's little tiny bits of variation in our curve, but overall, pretty negligible when compared to our cobalt. What this suggests is, of course, our cobalt is going to be a great quencher, and our oxygen is perhaps a quencher, but at a much more minuscule scale. So what can we do with this? Well, like I said, preliminary study, this quencher is something that we're looking for that's going to be more sustainable to work in these larger hydrogen-producing reactions. This cobalt is something it's not toxic, it's not really that hard to make. My colleague, Victoria Bamigboye, who's she's not here today, but she's the one who made the cobalt for this project. And yeah, so we want to test a couple of other options similar to this. There's such a thing as copper dimethylglyoxine, which is a very similar molecule, except you take the cobalt, replace it with a copper. The only problem is it's not as soluble in water, and water is a pretty readily available solution to be able to conduct reactions in. There are a couple things with our study that we also are trying to replicate and just change for our future instances. Actually, as of yesterday, we did some more testing and updating to our numbers and things like that. We wanted to compare the oxygen quenching ability versus this again, but by introducing nitrogen in the water, which would basically push out the oxygen and prevent any quenching that is happening from occurring, which would just more definitively tell us, is oxygen reducing our fluorescence as well, or is it not? But those are still to come, because we have just collected the data. And one other thing is there's plenty of solvents to try this in. Like I said, water, readily available, usually pretty cheap, you know, but there's tons of things. You could do alcohol, you could do acetonitrile, any number of organic solvents are an option. This is the extent of our study at the moment, though, and we're excited to continue it. This was from last semester, and like I said, we're still doing some work on it now. So, be happy to take any questions. Thank you for your time.
Any questions for our speaker?
Yes, ma'am.
So what was the most difficult part, or there may have been more than one, about even achieving preliminary data can be really time-consuming, and it seems like that would, those are great results, but maybe it was kind of difficult
Yes.
to get there. So
Yeah,
what was
so
one of your
you're
results?
exactly right. It's it is difficult to achieve results even in preliminary things. As you can see, this was a semester's worth of work, and we have only a couple data points to show for it. So the biggest struggle we actually faced during the study was calibration and replication of the data. The fluorometer that we're using had some trouble to begin with. Midway through our tests, the lamp bulb had to be replaced in it. So we had to sort of scrap a lot of our data from early on and just work with what we had. And that was another thing about going back and retesting, verifying this data, and hopefully having a more calibrated fluorometer next time. Yes, ma'am.
When you were setting up your method, what was your inspiration for that? Or were you, was this part of your class?
It was not part of a class. It was inspired by one of the classes I took. Dr. Anusree Mukherjee taught advanced materials classes that banked on some of these things with phosphorescence and such. But the inspiration came from some papers we read, and this is sort of a hot topic as people are always looking into better alternatives for energy. Like I said, fossil fuels have negative consequences in a lot of regards, and the clean energy sources we have either aren't sustainable or they're not very efficient. And so this is just another method. It's newer. There's not as much research on it as things like solar energy or wind, things like that. So that's why we chose to look about these things. And the rest of our inspiration came from literature on how people had done it and just modifying it slightly. Of course. Yes, sir.
The rose mingle, do you know what its half-life is, how stable it is?
I don't know that right off. We could find it. There's a lot of literature on it, and there's good data on it, but it's not something I know off the top of my head.
I know a lot of times fluorescent dyes, they seem to have fairly short half-lives, like over a couple.
Yeah.
That's really
I will say one of the fun things. I wish I would have included the picture on here, but I didn't quite have the space to arrange it. And this is tangentially related, but the rose mingle super vibrant peak. As soon as we added our 10 equivalents of the copper dimethylglyoxime, instantly, like within like a second, it just all turned from pink to like this faint tannish yellow color. It was awesome. It was like the best part. It was like what I did right at the end. And oh yeah, I'll have to get these pictures up here when I update this.
There's no more questions. Let's give a round of applause.